Hello, welcome back to the online course on fundamentals of composites and cellular materials. So, in the last class, we discussed about interfacial shear strength measurement. Okay. How do we measure interfacial strength in composite materials, that we discussed in details. Okay. And then we started talking about a case study where the composite material is basically Al-MWCNT nanocomposite. That means the matrix is aluminum and CNT is the reinforcement, and our aim is basically to understand the interfacial phenomena in such composite materials. Okay. So, I discussed about this particular slide that the idea is to make a nanocomposite, that means where the matrix is nanocrystalline and also the reinforcement particles are of nanometric size range. So, that we can enhance the strength from both directions. That means, reinforcing the matrix with high strength, high hardness, high Young modulus material, which would increase the strength of the composite material, and secondly also let us have the matrix which is nanocrystalline. By virtue of Hall Page relationship, there will be increasing strength. So, that is why this particular example has been chosen here, and the matrix is selected as aluminum silicon alloy as I mentioned earlier, because of their certain mechanical properties, and has been reinforced by carbon nanotube. As you can see here, as I discussed in the last class also, that carbon nanotubes are nothing but basically graphene sheets, where the carbon carbon bond is basically sp2 bond, sp2 hybridized bond, and these graphene sheets are rolled, so that you get a tube, and the diameter of the tube is in the nanometer range. As you can see here in this particular schematic, how a graphene sheet could be rolled to make a carbon nanotube, and then you can see here a TEM image of carbon nanotube, multi-wall carbon nanotube, where this is the hollow inside, and then you have the different layers of the graphene sheets, making it a multi-wall carbon nanotube. And multi-wall carbon nanotubes are having extremely high strength and modulus. So, these are obviously very good candidate to be used as reinforcement for high end high strength composite materials. Okay. So, and then how this composite material is made, I discussed that it has been made by a thermal spraying technique, which is called plasma spraying. So, in plasma spraying, the heat source is a plasma which gets generated by two electrodes. As you can see here, this is the tungsten cathode, and then you have this copper anode. So, a bias voltage will be applied between these two. So, an arc will be produced, and then there will be plasma gas, which is basically nothing but argon inert gas, and it goes through it, and because of this arc, the argon gets ionized, it creates plasma, and the temperature of plasma is extremely high. As you can see here, it says here in the range of 10,000 to 15,000 Kelvin, and then this powder is faded here. So, powder is fed here. So, ultimately the powder moves at a very high velocity through this heat zone and collects or absorbs certain amount of heat, and then ultimately it gets molten or partially molten. There is a substrate on which it gets deposited splat by splat. That is what plasma spraying is, and this technique has been actually applied to make the composite material in this particular case. And as I shown earlier also, that these are matrix powders, aluminum silicon alloy powder made by gas atomization. That is why these are spherical powders, and then carbon nanotube also you can see here. Okay. The diameter is in the range of 30 to 70 nanometer. Okay. So, now this has been mixed together, these two powders have been mixed together, aluminum powder and carbon nanotube has been mixed together in certain proportion. In this case 10 weight percent carbon nanotube was taken, and then 10 volume percent carbon nanotube was taken, and then it has been actually sprayed by this plasma spraying, and then by a special technique the deposited coating or deposited material was removed from the substrate. So, here is the substrate, from the substrate the deposited material was removed. So, then what you get basically a composite material here, standalone composite material which is basically, in which case the matrix is aluminum and it has been reinforced with carbon nanotube. So, now once you make this composite material by plasma spraying, then you need to look into the microstructure to see carbon nanotube is going through a very high temperature. So, is it really retaining its structure? So, that is why the first evidence or proof is that as you can see here, typical plasma sprayed or thermal sprayed structure, you can see this layered structure, okay, splat by splat the powder particles, molten powder particles have been deposited here. That is why you see a nice wavy splat structure, and then at high magnification also you can see this is the splat layers, individual splat layers, and in between individual splat layers you also can see carbon nanotubes are actually residing in between the splats. Okay. So, clearly you can see these carbon nanotubes are actually residing in between the splats. That means, carbon nanotube is there. Okay. And also you can do actually Raman spectroscopy ultimately to find out that if the structure is retained or not. So, you can see here that this is basically the CNT, the pristine CNT, which was used as reinforcement, and so typically they will be having two signature lines in graphene structure. One is called the G band or G line, other one is the D band or the D line. Okay. Now, this CNT intrinsically has lot of defects, and then you can see here after the the composite is made, there also you can see those two signature lines. Obviously, D line, the D peak intensity is little higher as it goes through a lot of high temperature, and also before plasma spraying it, it was actually ball milled. So, that the powder mixture was ball milled for long time to achieve good mixing, because nanoparticles, nanofibers, they tend to agglomerate. Okay. So, here the basic technique was applied, which is basically mechanical mixing was done here to achieve homogeneized mixing or homogeneous distribution, homogeneous distribution of the fiber particles in the matrix. So, it goes through high temperature, it goes through high energy ball milling also, and that is why there is some amount of defects gets incorporated once the composite is made. All right. But ultimately what we can see that CNT is retained. You can see also fractured surface, we can do TEM, ultimately we can see all these things. In case of SEM we can see there is nice distribution of the carbon nanotube fibers in the solidified matrix, and also you can see this kind of pull out CNT pull outs you can see, which basically signifies good fracture strength of the matrix material. Okay. And then ultimately actuators measured how much MWCNT has been retained in the matrix, and it is around 5.67 or basically 6 volume percent of the CNT was retained in the matrix. From 10 volume percent it has reduced to around 5.67. Okay. And also you can see in the TEM, you can see along with this CNT particles, you also can see primary silicon, and primary silicon comes from the aluminum silicon alloy. So, those primary silicon particles will also act as reinforcement. So, that is why it says here CNT short fibers plus SiT particulates both will be giving reinforcing effect, and also you can see here bundles of CNTs coming out of the matrix. Okay. We can see some amount of agglomeration as well, but the bottom line here is that even after going through that high temperature and of plasma spraying, and before that high energy ball milling, the CNT structure is more or less retained. Okay. There is some defect density, there is some defect has been generated, but still more or less it is the CNT structure, atomic structure is retained. All right. Now, our aim is actually to understand the interface. Now, pure aluminum shows poor wettability on non-reacting surface. Okay. For example, if you remember when I was talking about wetting angle hysteresis, where we showed that when you have a graphite surface on which aluminum droplet is there, and then with time we see initially it shows very poor wettability, or the wetting angle is extremely high, very high, in the range of 150 160 degree, and then with time aluminum reacts with graphite, it forms aluminum carbide, and because of that reaction the wetting angle gets reduced from a very high value to low value like 50, 60, 70 degree, in that range. Okay. So, and that is why pure aluminum does not show good wettability with non-reacting surface, but it shows excellent wettability on graphite surface with carbide layer formation. Once the carbide layer forms, aluminum carbide forms, on aluminum carbide aluminum flows quite nicely, or basically the wettability of aluminum carbide and aluminum system is very good. Now, in this particular case, in case of CNT reinforcement, the carbide formation is not possible as such theoretically. Why? Because carbon nanotube, this graphene sheet can be actually ultimately rolled by two ways. One, you can roll in this XY like this, or you can roll like this. In both cases, you get these two structures, armchair and zigzag. So, one basically gets rolled in the 100 plane, and other case, in zigzag case, it gets rolled along the 110 plane. Okay. Now, what is the importance of these two planes? Why I am talking about these two planes? Because this 100 and 110 plane, these planes are called prism planes in graphene structure. Okay. What is the big deal about this? Now, the carbide which forms on graphite or on graphene sheet actually grows from these two planes, one is either 100 or 110. Okay, you can see here which one is 100, this one is 100, and this the other plane is 110. These two planes, on these two planes, carbide starts growing. Now, if you are making it closed by making this kind of tubular structure, then this 100 or 110 plane are not available, right, in ideal scenarios. In ideal scenarios, you are actually closing either of these planes. Okay. So, the probability of carbide formation is extremely less in defect free carbon nanotubes. That is very important. Okay. If it is an ideal structure of carbon nanotube, then this kind of carbide will not form, but then in our case carbon nanotube contains already lot of defects. Also, we have seen that as it gone through high temperature, high energy ball milling, it actually created certain amount of defect in the carbon nanotube structure, graphene structure, as we have seen earlier from the Raman spectroscopic result. So, it has certain amount of defect, and those defects could lead to formation of carbide. And these are all predictions. Let us see what is happening actually. Okay. So, once we know that yes, there is a probability of carbide formation, though the chance is less, but in our case because of the defect density carbide could form, the next thing is to check which kind of carbide, because we have in our alloy we have aluminum and silicon both. Okay. And silicon is in quite high amount in this particular case, hyper-eutectic silicon, hyper-eutected silicon alloy. So, that means aluminum silicon alloy, silicon is in the range of 21% if I remember. Okay. Now, that actually you can see here. So, you want to see which case, I mean which carbide formation is energetically favored, thermodynamically favored. So, all different kind of carbides you can actually ultimately plot the free energy curves, and you can see this one coming from beta silicon carbide, the lowest energy requirement, and then you have this green one coming from aluminum carbide. So, these two are the easiest to form from the point of view of thermodynamics. All right, let us move on. Now, let us understand the growth kinetics. Now, what is happening here? You have MWCNT and then you have molten aluminum silicon alloy. Okay. Now, here in between this aluminum silicon alloy and then this CNT surface, this carbide is growing. If I consider that because of the defect density some amount of carbide will be forming, and we have actually checked earlier from the thermodynamics that the probability of beta SiC formation or beta silicon carbide formation is easier or more feasible, most feasible, then let us consider that SiC is forming in between these two layers of molten aluminum silicon alloy and MWCNT. Now, the idea here you can see here that because of the diffusivity of carbon is higher than silicon, carbon will diffuse through this layer, it will reach here somewhere here, and silicon will come from the alloy, and then they will react, will form the silicon carbide. Okay. So, there are two kinds of growth of the silicon carbide layer. One is this perpendicular growth, and other one is the lateral growth. Lateral growth means aluminum silicon alloy is coming here, and then you have this available free surface on which it will react and will form the carbide layer. So, the growth are in two direction. One is the perpendicular direction growth, which is completely dependent on the diffusivity of the elements, and then you have lateral growth, where lateral growth is much more easier because you have free surface available, aluminum silicon alloy coming here, seeing a free surface of graphene layer and forming the carbide. Now, at a particular thickness, which we are calling as critical thickness, okay, this thickness would be so high then that the diffusivities will be negligible, or there will be no basically diffusion or negligible diffusion of the silicon atoms or the carbon atoms as well. And in that particular instance, of critical thickness, this perpendicular growth will stop, okay, and only the lateral growth will take place. So, critical thickness is important in the aspect that is the thickness where the growth in the perpendicular direction stops. And why we are interested about this particular critical thickness? Because we do not want the carbide to be thicker, because as you understand, carbide phase is a brittle phase. So, when we have a brittle phase in between at the interface, it will lead to easy crack, okay, and then from there crack propagation will start and failure will start. So, we do not want it to be quite thick, we want even if carbide is forming, which is improving the weightability, because carbide formation is required, we cannot avoid that, we cannot neglect that, because carbide formation improves weightability, but at the same time we do not want carbide to grow also to a very high thickness. So, let us check what kind of critical thickness values we are talking here. That also you can calculate using an equation has been shown here. So, this is a very ultimately a short equation. You can come to this equation by doing certain calculations, but ultimately T critical can be calculated by using this equation. And you can see here the plots have been shown with temperature, the critical carbide layer thickness varying with the temperature. You can see here SiC does not really change, the growth of SiC does not really change with temperature, and for aluminum carbide also there is initially quite low value and then it increases, but you can see for silicon carbide layer it is almost 0. That means, after attaining 1 or 2 nanometer layers, 3-4 nanometers thickness of carbide formation, the perpendicular growth or the thickness increase stops, right. That means, it is actually good. So, the carbide layer is helping the weightability as well as it is not growing in the perpendicular direction for long time. It is showing low thickness, which is good from the point of view of mechanical strength. Okay. So, here is a schematic which shows how it is happening. So, there is MWCNT, on top of that you have this aluminum silicon liquid droplet. Now, initially as it sees this aluminum silicon layer or alloy, it shows it sees the CNT surface or graphene surface. So, initially the primarily the theta primary value or theta initial value is quite high. Now, as the moment the SiC layer starts forming, and I am talking about only SiC here, I am not talking about aluminum carbide, because we discussed that thermodynamically silicon carbide formation is more favorable. And we also realized that the critical thickness of SiC is actually lower than the aluminum carbide. So, in all practical purpose, let us consider SiC is forming on the surface. Now, as SiC forms keep steadily, and as we discussed, it achieves critical layer thickness. So, that means there is not much perpendicular growth, but it is actually growing in the lateral direction. Now, what is happening? This aluminum silicon liquid droplet is now trying to flow over the silicon carbide surface, not on the surface of the graphite or the graphene surface here. Okay. The moment it sees the silicon carbide surface, the wettability improves or the wetting angle comes down, as you can see here. So, a steady state is achieved where aluminum silicon droplet or the liquid aluminum silicon will be flowing over or spreading over the silicon carbide only. It will not be flowing over MWCNT or graphene layer or graphene surface. So, obviously, the theta value or the wetting angle comes down. Okay. So, you can see here from around 150 degree initially to it comes down to around 40 degree. Okay. So, that is the beauty of formation of silicon carbide. The point here is that silicon carbide is forming, which is improving the wettability. At the same time, from the critical layer thickness calculation, we realized that the silicon carbide layer thickness will also be not very high. It will be remaining in few nanometers, couple of nanometers, and that would be also helping in the mechanical, or actually it will not be really hampering the mechanical property of the composite material. As I mentioned earlier, if we have carbide layer growth at the interface, because of its brittle nature, the crack propagation starts from there. Okay. But in this case, if you have only few nanometer layer of SiC, that will be giving some kind of bending ductility, and it will not really be fracturing that easily. Okay. So, now all this what we are discussing are all theoretical predictions. We need to have some evidence. So, the first evidence you can see is an SEM image, where you can see a rope of CNT, that means a bundle of CNT together acting as a bridge or basically holding these two sides of the matrix. Okay. Now, this diameter of this rope is around 200 nanometer. However, our CNTs were in the range of 40 nanometers. That means, it is a bundle of carbon nanotube which has been basically nicely layered by solidified aluminum silicon molten alloy. Okay. So, that is the first instance of good wettability. You also can see in TEM, see this kind of carbon nanotube coming out, and then if you concentrate on the surface, you can see this SiC layers on top of the MWCNT surface. So, you can see here this thickness is around only 5 nanometer. Okay. So, that means, the bottom line here is that carbide layer is forming on MWCNT, though it is ideally not possible as the prism planes are not available, but still it is happening here. MWCNT on top of MWCNT surface, carbide layer is forming because of the defect density, intrinsic defect density in the carbon nanotube. That leads to carbide formation, first point. Second point, the carbide which is forming is basically silicon carbide. Thermodynamically it is more feasible than the other carbide formation, and also we have seen from here, from the TEM images and other data, that it is actually silicon carbide. So, that is the second point. Third point, the carbide which is forming, its perpendicular growth is not very high. As we calculated that the critical layer thickness of silicon carbide is quite low, and also we are seeing from this particular TEM image that the growth of silicon carbide is also you can clearly see that it is quite low, in the range of 5 nanometer, growth in the sense growth in the direction of perpendicular direction. Laterally it is growing over the MWCNT surface. And then you can do all kinds of atomistic simulation to actually see which planes are matching with what plane. So, this is actually a typical graphene layers, as you can see here, okay, 001 plane graphene layer, and then this is a silicon carbide crystal structure, okay, beta silicon carbide crystal structure, and then you can actually have this particular plane 001 plane of silicon carbide so graphite layer, and let me go to the next one, and one plane of one plane of SiC. So, 001 plane looks like this, and one plane, let me see if I have the image, okay, it is here. So, you can see one plane will be looking like this of SiC. So, this is also hexagonal. So, both are hexagonal structures, and there is some amount of atomic mismatch in the sense because of the lattice mismatch, there will be some lattice mismatch. You can see here, you can try to actually match them together. There will be obviously a good amount of lattice mismatch, around 24% and 26% in x and y direction, but still because of the hexagonal structures, there will be growth of silicon carbide on 001 plane of the graphene layer. Okay. So, ultimately, with that I would like to conclude here that we have discussed the interfacial phenomena in aluminum MWCNT nanocomposite, okay, where the particular composite material was made or fabricated by thermal spraying. So, aluminum particles, aluminum silicon alloy particles, powder particles, and then carbon nanotube, multi-walled, those were mixed together, and those were sprayed by plasma spraying to make this particular composite material. And then in the composite material we observed that there is good wettability by the matrix on the MWCNT surface by certain factors. Carbide is forming, basically there are again three factors. One is that beta silicon carbide layer is forming. So, carbide is forming because of the intrinsic defect density, and beta silicon carbide formation is more favorable, and the thickness of this carbide layer is also quite low. Now, once the carbide layer forms, that improves the wettability. At the same time, because of lower thickness of carbide layer, it does not hamper the mechanical properties as well. Okay. So, this is one way of how to analyze or how to understand interface in composite materials. Okay. In the next few classes, I will come with some more examples just to let you know that how actually we should analyze interface in composite materials. From the beginning of the interface chapter, I am mentioning that understanding interface is the most important part in composite material, because all the properties are basically dictated from the interface point of view. The load transfer takes place through interface. If you talk about delamination, that also happens through interface. So, we need to understand interface in different kind of composite materials in different systems. It could be MMC, it could be CMC, how the interface is playing role in ultimately improving certain properties, that we need to understand. Okay. So, with that I would conclude. I will come back again with some more examples. Thank you all.